Welcome to another video. Today we're going to talk about fine tuning, and I will go through one of my Kaggle project which I have done. We will do classification and fine tuning with EfficientNet. And before that, let me give you some little bit idea of fine tuning. So fine tuning is that you classify top of the column data set, but also basically you the weight import the weight of the pre-trained model, and then fine tune them. Okay, it is possible to fine tune all of the layer common net, or it's possible to an earlier layer. So either you can tune the all of the layers, and either you can, you first early layers could be fixed, that should be freeze, but the last layer should be unfreeze. That would be learned from scratch in that layer. The idea behind is that since the early layer detect the edges, detect the color, should be when you got early layers come with generic feature detector, ball protector, edge detectors. But in the when it's getting deeper in the layers, the model the model try to catch the actual detail of the images more progressively, and more specific details less yeah more specific details of the classes. And let me show you how to do this, and let me go walk through from this. This is a data set. First, I will import. I'm using pip install folder. I will show you. First step is we're going to import some of the libraries, and next step we're going to import the data. If I can zoom it, we will import the data and set the path. See, this will show the total number of the images. How much is that? We're using globe. It's a library. It will take all the images of the JPEG format. If you have data set which have another format, you just put that format path and you get the total images. Now we're making the series using data frame. Now we make a data frame. You can say generate a file name, total images, in which file name it will make the name of the image, and in the class field it will map the class ID. So over here we are going to check the total distribution of the data, that how much the data set contains. This class contain 1232 and this class contain 916. Over here this is plotly class go, and you can see that uh, I will show you the bars are created. Let me run it for you. You can see the different beautiful bars are created, and over here you can make the pie chart. Over This is the class head. Over here you will add the name of the classes, and over here you can add uh, total values for just counted from the names of the class ID and the name of the classes. So now over now this part we are using just split folder ratio, path of the folder, path of the data, the where it would be stored, seed, and the amount of data would be distributed. 80% would be training, 10% would be testing, and 10% would be validation. Let me over here Kaggle working output. Over here output you will see uh, when it's just working. Hold on. Validation test, data test, and train. See, now going back. This is over here we're setting the train path, validation path, and the path that I showed you earlier. Over here we're just counting the images of the thing by using globe. Again, using globe, setting the path and setting the format of the file, and then counting them. We have that this number of the images. Over here I just make a pie chart which shows the total distribution at 79.9% of data is of trained data, 10.1% test data, and validation data is contained 15%. This is again I want to see that how much data is splitted into trained data. So we make the trained file of the total train images. Total train images we get from over here. Total train images. Okay. And our total train images. Yes. Train imaging, make the series, make it a data frame, speed up process, and we got that in train dataset we have 985 images of this class and 732 images of this class. Distribution of the train data, again we are using y is equal to train.value classes. This one is this y distribution over train and y distribution over class. See, the same way you can just have the pie chart, and it is repeating. So I will share a link of the code and you can go to this part. Or not just quickly I will want to show you the fine-tuning process. So this over here I'm just displaying some of the images. Let me show you. See some of the images of both classes. This train, this part we just pre-processing data for data accommodation process, zoom range, width range, shift range, shear range, flow from the directory, target size, batch size, class mode is binary because since it's a two classes and they found images of two classes. So EfficientNet. I have made detailed analysis on the EfficientNet. You can watch over there. Over here we import the model, we specify the shape, we include top false, and we weight is equal to ImageNet. Now in fine tuning, either it is possible to train all the layers, but first step is a model.trainable is equal to true. Now over here what I'm doing, that I'm going to train just only last 15 layers. The rest of the layer it would be not trainable. And let me show you. Print the layer trainable. The rest of the train will be not trainable. See, false, 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 false. This layer is false, false, false. And over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. These 15 layers, if you can see, are trainable. Okay, and then I have added model.compile, adding the last flatten here, then drop out, and then dense over here. If you have multiple classes, over here you add the amount of the classes, that how much the number of the output on which it stored the prediction. Since it's binary, so we're using sigmoid instead of softmax, and binary cross-entropy, not categorical cross-entropy optimizer is Adam, and metrics are accuracy. And then and one interestingly, if you can show this, so EfficientNet are not a net, its base network is just net, and you can see the skip connections. See, skip connections. So EfficientNet is baseline net of the ResNet, and EfficientNet is the type of architecture which is scaled into 3 dimensions. You must watch that video in which I explain the paper in detail. And then you can visualize in this form as well if you have smaller architecture. I must say it would be not good to show that like this way. Early stopping is used for the callbacks if the model is not to prevent the model from overfit. It monitor validation accuracy, and it will stop when they find the maximum validation accuracy. And this is safe best only true. The model is safe. You can see over there. Now I've trained the model, and it already stopped at 31 epoch, but I initiated the model with 50 epoch, but it stops at 31. And over here you can just plot the graph of the loss, training loss and validation loss, and you can print the see accuracy down to 2.166. And over here I'm using test generator classes, and to predict the test generator it will save prediction amount, and then npload argument will store the maximum of that thing. That and this is classification report, and now we're making a validation data frame with which we have file name, actual, predicted. Actual is by validation, and predicted is by prediction, and we're just setting those things. Say file name, actual, predictive. If the actual file or predictive file is true. Over here we're going to make a function with prediction camp. It's just function is reading the image, load image. The load image comes from over here. You can see it's a built-in function, and then it's just displaying in this form. Correctly classify actual this class, predicted this class, actual this class, predicted this class, and this is a misclassification part, the thing which is not misclassified. And at the end we're using the y value y prediction for the confusion matrix, and this is confusion matrix code. And over here you can see confusion matrix is over there. So I will share the link of the thing. If anything you don't understand, you can thank me. Thank you.